Hello and welcome back to yet another lecture in the series of microprocessor systems design and interfacing course. And this is a very short lecture. This basically speaks about the subroutines or functions in assembly level programming. And also we will in fact I have introduced the freedom board to you, but we'll do a quick reintroduction so that if you didn't listen that time in the last lecture, it will be sort of a review on the board again. Okay, so that's the plan. So what is this subroutine? So we almost covered the entire instruction set, right? I mean, I just gave some sample examples from various scenarios which you could play with in the Keel Microvision software and then realize for yourself how things are changing. Hope you have done that. And there is only this small portion left where so far in all the previous lectures what we have done is we have written our program in one function, which is the main function, right? But that's not the way we generally write a program. We will have these modules or we have these functions, and then we repeatedly call these functions from the main function, so, right? That's the way we generally do in typical MATLAB or Python or C programming. The same thing can be applied in assembly language as well, and so that's what exactly we will be discussing this lecture. Okay, so without any further delay, let's jump right into the definition of subroutines. So subroutines in a block of code, right? It's a certain section of code that is called from different places from within a main program or other subroutines, right? So that's there is one main program, and then you, to make it modular, to make it look good, you write several subroutines and then you call those subroutines from the main program. So that's the essential meaning of this statement. And then of course what it actually helps you in subroutine, which you already know because you already taken courses in C programming, for example, is that subroutines help us to save space, right? Because you really don't need to, if something is really going to be repeatedly called, we can make it as a subroutine rather than again and again repeating that in the main function, because that unnecessarily increases the space of your main code as well as it doesn't look good at all. Okay, so it's very important that it saves that code space. It avoids redundancy because you can create a function, you can create a subroutine out of it and then call it many times in the main function. Okay, so that looks very nice. Yeah, and then of course we know that there is a big concept, right? I mean, you have certain variables and this concept of pointers, basically, where you essentially don't change the content inside the subroutine. And then there is global variable, local variable concept, where global variable is something like you will be able to change that in the function, and the moment it changes in the function of the subroutine, it gets changed in the main function also. So those things are actually extremely important. So here also we will understand that concept very clearly in this section, where it's important that you are careful in that, because please understand that when you write C program or MATLAB or Python, you are working very high level, right? But when you write programs in assembly language, you are really working in the register level. That's the lowest level that you could think of. Now you just imagine that you're changing a register. You have some value for a register in the main memory, and then you entered a subroutine, and inside that subroutine you accidentally change that register value. Then what's going to happen is, like, when it returns back to the main function, that value in the register is already changed. So that's very very important. So we will, I mean, there's a way out actually, so I will explain that how to go about it. Okay, and then of course we need to actually we need to return, right, from the subroutine. You need to return to the main function or return to the function from which the subroutine was called. So how to go about it? I think we discussed this briefly when we discussed about this concept of link register. So link register is definitely going to help you, so that is automatically done. But there are certain scenarios where you need to override and you need to come forward and save the coding. Otherwise it may get stuck inside a subroutine and will never come back to the function from where it is called. I have a very beautiful example in that direction. Okay, so it's important that the return is issued correctly. And then for that return, in the case of a assembly language, it is something like the link register program counter combination, right? Hopefully you remember that section which we discussed about the link register usage. If not, please go back. So what happens when a function is called from a main function? Let's say I'm in a main function and suddenly I'm calling something which is actually in a subroutine. So the program counter will get the address of the subroutine location, right? But then after the execution of subroutine, you need to come back to the location in the main code and keep executing the next few lines, right, after the calling of subroutine. So how does it happen? So basically, when a subroutine is called, the link register is your friend. Link register will store actually the current program counter value, and then program counter will get loaded with the subroutine address, and then you execute everything, and the moment you have the return reached, what is going to happen is the link register content will go back to the program counter, and so that you can execute what is the remaining code in the main function. Okay, so play with this whatever we are discussing, so that you understand that thoroughly. Okay, the best way to get used to it is actually do some coding and then understand that using the Keel software. Okay, so that's it. Space in data memory must be reserved for parameters, local variables, return value, all these actually, because the memory is the key, right? I mean, you go into a subroutine and then you have to come out of that subroutine and keep executing the code in the main function, because that's important. And for that to happen, you have to be careful about the local variables, return value, all these whatever we were discussing. Maybe too much of verbose there, but I will make you understand that with some examples. Okay, so this is key actually, even if you don't spend a lot of time in these lines, but this is extremely important. It's very important that when using subroutine, we need to know the following: what is the next instruction's address, right? And then the return address also we should know, because that is where you should, after the execution of subroutine, you should go back to that return address and then execute the things from there, right? Execute the code from there. Okay, so that's the key aspect. Okay, so let's move to some interesting example. Okay, so here is a subroutine. Let's see what it does. So some main function. So let's say this is a main function. Okay, and in this main function, what I'm going to do is I'm calling a subroutine. Okay, so let me use a different color here. So this is a subroutine. So branch loop, that means this guy will go and start executing from this label, right? But after executing, you should actually go back. I'm sorry. So you should go back and execute the place from where you actually sort of ended. Let me use this color. Yeah, so basically after this you should go back and start executing this. Okay, so let me actually use the flow color so that it's very clear to you. So the first step is actually from this statement, it will come and execute this, and then of course from this guy it should come and execute this. So this path should be automated. But then there is a big issue in this code. Okay, what is this issue? Is you just carefully see here, you have moved R4 some value which is 1, but inside the function you are actually moving R4 with 100. That means you're corrupting this register, because now no more in this section of the code, the value of R4 is 1, because you already changed that R4 to 100. So how to sort of overcome this problem? This is one of that local variable problem I was talking about, because R4 you are not supposed to change it inside the loop, because you are using it in the main loop. So how to go about preserving that R4 value? Because or make it simple. Let me make it simple. So the R4 has a value, but you're corrupting R4, that is okay, but when you return back to the main code, R4 should have the value 1. So how to make sure that happens? So in the classroom session I would have actually spent some significant amount of time discussing with you, but now you pause the video, just think about it. From all the instructions that you studied in the previous week, which instruction is going to help you out here? So the objective here is the R4 value when it returns here, okay, before this statement, the R4 value should change back to 1. So don't think of trivial way of saying, okay, you move R4 to somewhere else and then, I mean R4 to another register and then you swap it. That's not the way. There is a better friend for you from one of the instructions. Just think about it, and I will let you know the answer in a minute. Okay, so the answer is actually very yeah. Before even going to the answer, let me explain this part, which is extremely important. So when this statement is executed, what is going to happen is the link register will have the address of this guy. Okay, so this is the address which the link register will store, because after the execution of the code you should actually come back to this. So how to ensure that this is going here is very simple, because you are branching to link register, and what does link register has? Link register has the address of this guy. Okay, so it will go and execute this. Okay, and the program counter will have this address, because at this point I'm saying. So I'm talking about the execution of this particular line. What is going to happen is link register will have this address and program counter will have this address, and then of course at the end of the function or subroutine you are branching to link register, which is nothing but this address. So that's how everything keeps floating, or everything keeps happening. Sorry. Okay, so that's the thing. Okay, now I think even moving the that problem statement which I raised to you should be there in your mind, because I just deviated a bit now, and I will come back to that statement soon. Okay, so let's actually see the next step. So how will the function return a value? Okay, so that's extremely important. Okay, so this is sort of a consensus that is actually accepted in the ARM world, ARM world. Okay, where you generally use R0 to R3, those registers, for returning values, and R4 to R12 are used in subroutines, hence needs to be saved. Okay, so that's the important, it's related to the question I asked you before. Okay, so sorry, so R0 to R3, those registers are used for returning values. So that implicitly means that they should not be used inside a subroutine. So you should not be using those, so that you can ensure that they are only used for returning values. Okay, and inside the subroutine you will be using R4 to R12, those registers. Okay, but then the problem is, if R4 to R12 had some value which was there in main, the main function, then that values have to be preserved, because the moment you return from the subroutine to the main function, whatever were the original values in R4 to R12 should be kept as it is. So there is a need or necessity to preserve the moment it enters the subroutine. Okay, so again I will reiterate again, if I'm confusing you, the registers R0 to R3 are used for returning values from function. Suppose you want to return some value, which is very common, right? I mean, in C or MATLAB or Python, we generally return some values from the function, right? So the registers which are used for this purpose is R0 to R3. That means implicitly R4 to R12 are used in subroutine, used for some calculation purpose, let's say. But then the problem is, this R4 to R12 may be used in the main function also. The moment you corrupt these or change the values inside the subroutine, there is a problem, because the moment you return back to the main function, you won't be able to get or retrieve those values. So it's important that the moment you enter the function, enter the subroutine, you preserve all these values, particularly the R4 to R12. So it's a good practice. The moment you enter the subroutine, the first statement of execution should be to preserve these values, and that should be done in a systematic way. Now I am just giving you more and more hint how to go about it. So this is wrong, as I said, because R4 is corrupted here inside. So you have R4 overwritten by 100, that means this is lost. So how to go about it? It's a very simple, using your push and pop commands. It's something like this. So in this case I am using only R4, so that's why what I am doing is, immediately in the loop the first statement is push R4. Okay, so sorry. So the first statement is push R4, that means R4 value will be pushed to the stack, and before you branch to LR, you pop the content, that is the latest content in the or the last content in the push will be popped to R4. That means R4 value will be saved. So as I said in the previous slide, it's always a good practice to have the statement something like push R4 to R12 and pop R4 to R12, because in case you are corrupting those values inside the subroutine somewhere here in this part, if you're corrupting that, it's always easy to recover that value before you issue the branch LR command. I hope I'm not confusing. It's quite straightforward. The understanding here is R0 to R3 should be used to return values. R4 to R12 could be used inside a subroutine, but before using them, it's always safer to push them to stack, and then before returning to the main function, pop those values back, so that you are preserving the R4 to R12 content and not touching them, which are preserved while in the main. Okay, so whatever is there in the main, whatever written in the main should be actually kept as it is. Okay, so that's the concept, and now this is something which is interesting and real use of subroutine, right? Let's say I want to calculate r0 raised to 4, or you can say x raised to 4. Okay, some x, I want to calculate the fourth power of that x. So this is a code literally. So first of all, let's say I'm putting some value to, so r0 I'm putting as 2, so I move to r0, then I go to something like quad, and then I'm calling the square root. So this is basically a function which executes square root, so I'm going to call these 2 times. Okay, so that's the idea, that's what happening. So one time will be square, second time will be to the power of 4, and then of course I will return back to the main, and that's it. So, and if I map this entire thing to something like a label, and that label is nothing but an address, if I do that, you can actually literally see this, you can actually write the code and see whether these addresses make sense. So actually you can see a lot of things from here. So this is 8, this is A, that means actually 2 locations. So this is something like 16-bit address. Move as r0 hash 2 is a 16-bit instruction, sorry, not address, instruction. So that's why 8 is having the first part, and the 9 is having the second part, and 10 is nothing but A, which will be having BL quad. And if you see here, BL quad is a 32-bit instruction, because quad is an address. An address itself, we know that it is sort of very important to know that it is sort of 16-bit in this case. So that's why 16 plus 16 is 32. So you can see that A, B, C, D are going to take this instruction. So that's why E, the next instruction is at E. So A, B, C, D locations are going to occupy the instruction BL quad, and that essentially means A, B, C, D is like 4 locations. 4 into 8 is 32. So that's like BL quad is actually a 32-bit instruction, or in terms of ARM, this is the thumb instruction, right? I mean thumb 2 instruction. Okay, so that's the key concept. Okay, and again move as r05, again a 16-bit instruction. BL quad is again a 32-bit instruction, and B and L, interestingly, is actually a 16-bit instruction. Okay, so that's the thing, that's the important concept here. Okay, so the major takeaway from here is not this. Okay, there's some issue here. So what is the issue in this code? Okay, so you might be thinking, okay, I said everything, now I'm saying some issue is there. Okay, so can you figure it out? What is the issue? The issue is, I will give a clue. The issue is because we are calling BLSQ 2 times, and the moment you call BLXQ 2 times, what is going to happen? You can actually try executing this code. Even if I execute BXLR, it will never come back. Okay, so let me actually give the flow first. Okay, so let's do this. So this is done, this is executed, then BL quad, that means it will go and execute this guy, and then BLXQ, it will go and execute this guy, and then BXXR, it will go and execute this guy, right? And then again BLXQ, it should go here again, and then BXLR, it will go again, but then BXLR again, ideally speaking, it should have gone back, to this guy, right? Because that's where we started off. BL quad, it came here, so this is the instruction which should have executed. But the problem here is, now I already gave the clue, the BXLR, right, it is called 2 times. That means this BXLR will be always staying here. You can actually try this out. I will show you in a moment in Keel what is going to happen here. So let me actually again, to understand this, you need to understand that LRPC thing. Okay, the moment you call this function, two operations are happening. One is LR address. Okay, so let me use that pen correctly, give me a moment. Okay, so what I was actually saying is, at this point, the moment the branch is actually executed, okay, so when this is executed, what is going to happen is LR should have the address of this location. Okay, so this location, in the Keel there is a small change. This will not store the next address, it's just like one value less, because there's PC plus 2 or PC plus 1 will always happen right after, so it won't store exactly this, but for the sake of understanding, I'm going to take that example. So LR should have this address. So what is that address? So let's actually see this address. So this is the address of LR that should be having. So let me put that number here. So basically this guy 0 0 0 0 0 1 0 E, basically pointing to this guy. So that should have been the address here, and then of course PC will have this XQ, or not XQ, quad. So quad is basically this guy. So PC should have this address. Okay, 4 zeros, 0 1 1 A, which is actually corresponding to quad, because that's what the next instruction to be executed after this instruction, right? Because we are branching to quad. Okay, so this is like the value of LR and PC at this point of time, or this point of execution. Now what happened is, actually you, after this, the quad, because PC has this address, so it goes and execute this guy BLXQ. Now is the interesting concept. So it's again a branch. So what is going to happen is LR now should have what value? It should have SQ value. So XQ is basically this guy 0x. So that's a problem, because LR is gone. LR is actually updated with this particular value. You're going to call a branch statement without actually saving the value in LR, because then the LR is going to get override. So this will be basically 0 0 0 0 0 1 1 6, because this is the value XQ, right? And then PC, of course, as we know, PC will have the value of the next instruction, which is actually BLXQ again. So the same address will be here. Okay, now what is going to happen is, after this it will go and execute this guy, and then this will be executed BXLR. LR is this address, so this will come back to this particular address here, and then of course BLXQ again, it will go back here. But then the problem is this guy, this BXLR, this LR is basically this guy, and it's not equal to this guy, it's not equal to that, so it will never come back and execute this move RS R05. Okay, so let me actually put it in the term of flow chart, so that it's very easy to follow. So this is executed, and after this, let me put this way, this will be executed, and then of course at this execution this will be executed, then this will go definitely here, but then again this will be executed, this will definitely go here, but then the problem is this will remain here. It will never ever go back to this point, because you didn't save the value of LR. So let me actually show you the solution also. I think you already know what is the solution. Just like the previous case where we saved the value of R4, the solution is in this slide. Okay, you push the LR, the moment you enter this function, you push the LR, so that LR value is saved. You do everything, and then you pop it to PC. Okay, not pop LR, because I don't want to pop it back to LR, but pop PC, so that program counter will go and execute this guy. Okay, so that's the idea. So let's try this out in Keel quickly, so that it's easy for you to understand what I'm talking about. Okay, so this is the code. Let me just build it. Same code whatever written in the slide, I just kept it is as it is. So this is the code. So let's, I need not explain it, so it's self-driven. So the same code, but this is going to have an error, because it will never ever come back to the sorry, let me just go back here. BXLR, same code, it will never come back. So I think I didn't put it here, so let me just write BXLR. Okay, so that's the full code. I think it's ditto. If you want to check, it's exactly this code. Okay, now let's run this again. I think I added this, so I need to build it again. So please remember, when doing lab also, every time you change the code, please remember to build it, otherwise the previous version will be used. Okay, so that's very important. Now let me debug. Okay, so we'll quickly go to the main function. Yeah, so you are moving R0, so R0 is actually 2, and then you jump to BL quad. And I suggest you, when you do it in the lab or you on your computer, I suggest you to see the values, what is it jumping to the address location, all those things in detail. Okay, so it's moved here, BL quad, this guy moved here, then BLXQ will actually move it over here, then you're multiplying R0, which is done, then you are going back to LR, that means it will come back to this point, which is also fine. But then the problem is we didn't save the LR here, so it will never go back to this guy. That's the problem. So this again done. So result is fine, you are getting it. This is actually decimal 4, This is hexadecimal sort of 10, but it's decimal 4. That's what 2 to the power of 2 is 4, right? So the answer is here, but the problem is LR doesn't have this address location, this particular location, so it can never go back to there. So that's it. It is stuck here because LR is this address itself. It is just stuck here. Okay, now how to overcome this? Let me go out of the debug thing. Oh, sorry. And now how to solve this is go back to the function. Sorry. So go back to the function, and all we need to do is basically push. So you push the value of LR and then pop not LR but pop the value to PC. Okay, so sorry. So that's it. So now let me build it. Okay, so no error, and let me run it now. Hopefully this time it should work. Yeah, so this is done, this is done, that's also done. The result is actually 2. One more time it will go. So this is 4 now, and now let's see. So pop PC. I am here, I'm back here, right? So it's done. And now let's see R05 and then BL quad 5 square is 25. So let's see that happening or not. Yeah, so this is somewhat like whatever value you had, that value will be here, and that's it. B and L. So no problem here, and then NL is nothing but here, so it will come here. So there's no issue here. So what we did is a very small change. We push the LR value and we pop that to PC so that you are on the safer side. Okay, so coming back to lecture, I hope this issue you are already aware of it, and that's it. So this is a very small crisp section on the subroutine. I just want to conclude by reintroducing the freedom board, which you will be using in this week's lab. So it's very important that we once again get familiarized with this. So I just reiterate, the major processor is actually right here. The 128 GB KL25 is at the freedom board. It is actually right here. And then you have a debug section which you will be using to debug, and that is actually in this part. Okay, so let me actually tell you. I think it's almost like this. So the port here is this port, which is what you're going to use, the SDA port. Please if you should not put the USB cable here, but it should be here. This is a debug path for us. And then just to reiterate the other options that we have over here, there is an accelerometer which you can see over here. There is an axle which is the accelerometer. This is your tricolor LED which you will be using for some experiments in the GPIO, which is in the next week. Then you have a touch screen which is here. Okay, so this is a capacity touch screen which you can use for many applications. Okay, and that's, I think the major components are that there is a reset button here. So in case you program the board and it is not working, just press this reset to ensure that you are sort of reloading the program. Okay, so that's the main part. I think, yeah, the input output connectors are here, which will be sort of soldered for you. So you may not see as whole, but the connectors really are placed there. Okay, so you can see the coin battery probably on the other side. It's not visible here. On the other side of the board you may be able to see that. Okay, so that's it. And then, yeah, the peripheral wise, so what is inside our board, this is what we have in a more detailed fashion, and this is what we will be learning in the subsequent sections. So you have the Cortex M0 Plus core here, which we already discussed a lot. Then you have the memories, the memory map also we discussed a lot. Then this is the GPIO, the human machine interface. HMI is nothing but human machine interface. So you have the touch sensing, which I was talking about, touch sensing interface. GPIO, which you have a dedicated section in the next week. And then a lot of clocks, actually, a lot of clock options are there. Okay, then timers. So pulse width modulation, timers and interrupt, you will discuss again one session dedicated to that. So we'll discuss that. Analog to digital conversion, we have one session dedicated to that. So this is to interface all the sensors that you play with, the analog sensors. Then the communication, the serial protocol, we will discuss about I2C, we will discuss about SPI, and we will discuss about universal asynchronous receiver transmitter, which is UART. These three things we will discuss. and these are advanced stuff, you may not be discussing that. And then of course this is some system level, this is also for a higher level microprocessor or a computer architecture course, something like we will briefly discuss about DMA, direct memory access. So that's an interesting concept worth understanding. So I have a session, there's no practical on that, but there's a session which will be discussing on that. So this is like the interfacing part. So far we are looking inside the microprocessor, basically at this part the processor, the which includes the register memory and so on. Then we have a session on interrupt controller also coming, and you will be learning about the debug interfaces in the lab as well. Okay, so with that we will stop. So we will start the lab also this week. Hope you come prepared. Please go through all the videos till now, particularly on the microprocessor ARM microprocessor side, Cortex M0 Plus side, so that you understand that. Please download all the necessary documents in your laptop and come prepared after installing the Keel Microvision and the PE Micro Debugger, which is actually the one which we will be using to connect the board to our system. Okay, so see you all in the lab, and hopefully we'll have some fun time there. Okay, so that's all. I think I'm not going to have any other lecture this week because we will be starting with the interfacing next week. Okay, so see you all in the next week for the video lecture. Till then, it's goodbye from my side. Thank you.